Okay, so let's get started. So good morning, good afternoon, good evening. Thank you for your participation and welcome to the second session of the Access to Space All second Systems Engineering webinar series in cooperation with NASA. My name is Mami Sasamura, expert of the UN Office for Outer Space Affairs. Today is the second session of this webinar series, so I believe most of you are familiar with this, but this webinar follows the first series, and it's designed to provide a more in-depth focus on systems engineering principles to help you develop small space missions. And we will cover 4 topics in total, outlined here, related to fundamentals of systems engineering and project management. We are the second one about the project life cycle review today. And after today, we will have 2 more sessions in January and February next year. So before we begin, I want to explain a few things. First of all, we would like all of you to keep your microphones and camera off during the lectures. But we will open the floor for questions after the lecture, and there you can turn on your microphone and ask questions. But when you do that, please raise your hand so that we can make sure to do it in order that comes up through Teams. You can also write your question in the chat. We will be picking up questions from there too. Second, the presentation and the recording of today's webinar will be posted on the UN-USA website in a few weeks. We made the same announcement at the first session, but it is taking more time than expected, so we have not been able to upload the recording for the first session yet. We will share the URL as soon as it is ready, so please wait a little longer. And you can see the QR code and the URL here to access the presentation and the recording data. Third, if you are active on SNS, please use the hashtag Access to Space for Systems Engineering webinar series and follow, like, and share UN-USA and NASA to help us promote this event. So from here, I'd like to invite Dr. Craig Buckhart, NASA Small Spacecraft Systems Virtual Institute. He will introduce today's speaker and moderate the Q&A session. So I will now turn it over to Craig.
Thank you, Mami, and welcome everybody to the second webinar series today. So today we have the speaker, Dr. Butler Hine, who is the Space Flight Project Manager at NASA Ames Research Center in California's Silicon Valley. Butler has held a number of technical and management positions and is currently the project manager for NASA's Helioswarm mission, a novel swarm of spacecraft that will investigate the physics of turbulence. Dr. Hine's background includes work in spacecraft design, flight software, and avionics, information systems, radio and optical astronomy, optical instrumentation, machine vision, robotics, and information visualization. His research interests include low-cost spacecraft designs, avionics architecture, embedded systems, space telerobotics, image processing, machine learning, machine vision, and 3D visualization. So welcome, Butler, and the floor is all yours.
All right, thank you, Craig. Let me share my screen. All right, well, hello, everybody. As Craig said, I'm a flight project manager at NASA Ames Research Center, which means that I manage a variety of flight projects. My background includes a range of sizes of missions, and I'll go into that a little later. But what that means is that I'm familiar with both the very small team skunkworks approach to missions, and all the way through the very large missions that NASA does, where it's a large team. It's big spacecraft, big instruments. So I have a perspective on that range, and can convey some insights I've had over my career about what works against the different mission sizes. So an overview of today is we're going to discuss the project lifecycle review process, and I'll be focusing on what NASA does in this domain. Although there are different approaches, and towards the end of the talk, I'll talk about some of the other approaches that we're investigating right now. But I'll describe what the elements of project lifecycle phases are, and then what we do in each of those phases. And then we have key milestones within the phases, including the lifecycle reviews. And then the criteria to transition to the next phase. And then I'll briefly talk about how systems engineering and project management play a role in the different phases. So the fundamental elements of the project lifecycle phases are, and this is NASA terminology, but it does, the intent does apply across the board to other missions, and the international community uses a very similar approach to this. So I'm most familiar with the NASA approach, so I'll describe that. So at the beginning of a project, we have the pre-phase A concept studies phase, and that's where you're getting your idea together. You're trying to see if the mission is feasible. And then once pre-phase A is completed, so you know you have a viable mission concept, then you go into the concept and technology development. We call that phase A. And this is where you're in pre-phase A, you had typically limited resources. So in phase A, you'll go into more depth on the design. You'll investigate your costs and determine your schedule. And then that leads you into phase B. Phase B is where you're doing your preliminary design, and you're also completing your technology maturation. If your mission does need to mature technology, by the end of phase B, you want that to happen. In phase CD, that's your hardware phase, your intensive hardware phase. So phase C is where you're finalizing your design, you're ordering all of your flight hardware, and then you're assembling everything together. So you're finalizing the design, doing your analysis, assessing your margins, et cetera, and you're collecting, either fabricating or buying all of your flight hardware components. And then phase D is where you assemble your whole system. And the intense activities during phase D is the integration and test activities. And that culminates in the launch of the mission. NASA, we do have other phases beyond phase D. We have a phase E, which is our operations phase. That's where you're operating the mission. And then we have a phase F that is the end of the mission, where you're decommissioning your spacecraft and instruments and closing down the mission. So those are the elements. And then I'll go into these a little more. So as I mentioned, the first kind of gate, we call these gate reviews because the way NASA uses them, they serve as a stopping point before you move to the next phase. And you don't really stop, but you kind of, the project does a self-assessment, and usually we have external review boards that are assigned to the project. Larger projects have what are called standing review boards, which is a set of experts in the different domain areas involving spaceflight. And those review boards will assess us assess a project at each gate review. So phase A, we'll do a systems requirements review. And that's where we always do system requirements flow down to, it's a system engineering discipline. You may have heard about it in the previous webinar at length, but this is where we organize all of the requirements that we need the mission to accomplish. And it's I used to refer to the requirements as a checklist. It's and it's more complicated than that, but it's like a tree of identified requirements that you start from the top and you flow them down to the mission elements. And so you'll start at a very high level requirement, that is the measurement that you want to do. What is the science or technology demonstration, or what is the measurement that you're trying to do, or the data you're trying to obtain from the mission? So that's obviously a top level requirement. And then you'll have a requirement that is must fly in space, and that sounds kind of obvious, but that top level requirement, you then break those up into smaller elements. And for the data requirement, that will decompose into things like what types of instruments do you carry? Where do you have to fly to take that measurement? Is that a measurement that you take in Earth orbit? Do you need deep space? Do you need to be around the moon or around Mars? Is it a landed mission? So the type of data you're going after determines where you have to go. But flying in space by itself is a requirement that drives you into the need for a spacecraft, into the need for a launch vehicle. And then those decompose into elements below them. So once you know you need a spacecraft, the science requirement tells you where the spacecraft has to go. And then the spacecraft decomposes into what type of propulsion system does it need? What type of power does it need? Does it have a requirement for fine pointing? Some missions do not require fine pointing. Others depend entirely on fine pointing, such as astrophysics missions. So also the destination for the data measurements also determines your communication system. So communicating with things from Earth orbit is relatively simple compared to deep space. And then once you get into communicating from Mars or beyond, it gets more and more complicated. So you can see that a key thing that is the gate into phase A is the system requirements review, because that is where the project will go over the requirements with the review board at what's called level 1, level 2, and then driving level 3. So these are the top level requirements. We clarify our very top level requirements. We decompose those into system level requirements. And then we also, at this point, identify what are the difficult or driving requirements that will face the mission below them. Because once you get into a requirement like we must fly an imaging instrument, and we must fly a spacecraft. So those by themselves are requirements. But then if you decompose that into what is the image you're going to look at, you may find that you have a driving requirement. The driving requirement can be, pointing. We talked about pointing just a minute ago. So that's where you identify your top level requirements and the driven requirements. And then you go into phase B. And phase B is where you really do your preliminary design in depth. And if you need new technology, you complete the technology. And that review culminates in the preliminary design review, or PDR, at the end of phase B. Now, in the NASA world, the PDR is a very critical review, because in the NASA world, pre-phase A and phase B are considered the concept phases. So this is where you're proving your concept will work you're doing the analysis to ensure that your mission closes technically and that is likely to succeed. And so in the NASA context, until you get through PDR, the joke is that you're presumed guilty unless proven innocent. So in up through PDR, the assumption is skeptical that will the mission close? Is the mission technically feasible? And so you have a high bar that you have to go through to prove that that's correct. And that culminates in what in the NASA world is a key decision point. Most of our gate reviews have key decision points. And in this one, after PDR, there is a very big key decision point, which is called confirmation. And that's where the mission is approved by the stakeholders. And the stakeholders are the NASA headquarters has directorates that control different aspects of what we do. And one of those is the Science Mission Director. We have others. We have aeronautics. We have human spaceflight. We have other mission directors. But in this context, for instance, if it's a science mission going to Mars, then Science Mission Directorate will hold a KDPC, a key decision point, and confirm the project to move forward. And that's also the time, the gate after which the project will start spending significant money on flight hardware. So up until that point, during phase B, you're developing your technology. If you have new technology that hasn't been proven before, you'll develop and test it and prove that it's ready for flight. And then you do a lot of analysis. And then once you get through that key decision point after PDR, that's when you're authorized to spend a lot of money. So you're actually buying flight hardware. So at that point, you transition from the concept phase into the development phase because you're now developing your hardware. So once you're in phase C, you've gotten approved. These phases, say CD, instead of phase B, where you're guilty until proven innocent, in this phase, it's more the reverse. You are assumed to be viable until and unless you run into a problem that shows you can't do the mission. So in this phase is phase C is where you're doing your detailed design closures, and the goal of closing this technical design is to allow you to quickly purchase flight hardware or fabricate flight hardware if you're doing that in-house inside. And so at that phase, that's where you're ordering your flight hardware, you're finalizing your design, everyone's agreeing to their interfaces. That's a key point in system engineering, is to identify and document the interfaces between your systems and also between your subsystems. So that's where you're, for instance, finalizing the command and electrical interface between your avionics and, say, your propulsion system. That's where you're nailing all that down, because you have to have that nailed down in order to purchase the flight hardware. You order your flight hardware or you start building your flight hardware. And then phase C culminates in a critical design review that is our gate to allow us to proceed with full-scale fabrication. So that at that point, your interfaces are completely mature, your design drawings are mature. Basically, all aspects of the technical design are mature to the point that you can actually order or start building the thing that you need. So you order your radios, you order your avionics suite, you may start building your propulsion system or ordering it, depending on if you're buying that or making it. And so that's the gate where you're actually committing to your hardware. And then for phase C for CDR. And then at that point, you also start getting your hardware in. So you order hardware, you start getting it in phase C. You gather all your test data. If you're doing testing on components, flight hardware components, you'll do your testing on the components. And the goal is that by the end, you've got a complete set, hopefully complete. Sometimes things are very late, but you'll have a complete set of components that you can start pulling together. And that's when you go into phase D. So phase D is where you're doing the system assembly, integration, and test, and it culminates with launch. So in phase C, you may have pulled together your major systems. So for instance, your science instruments, by the end of phase C, your science instruments are completed, they've done their own testing, and you're ready to go. You also may have completed your spacecraft. Sometimes spacecraft completion happens in phase D, but the goal is that your spacecraft might be completed by the end of phase C. But phase D is where the major components come together. And that is, there's a review that we will often have in here that's not really, it's not called out in these charts, but it's a review called Systems Integration Review. And that is a gate review that NASA uses when we have all of our systems together. So at that point, all the systems are potentially reusable. So if you have a science instrument that's intended for your mission, it hasn't yet been integrated into something else. And so SIR is where we will decide whether we're ready to do the major system integration. And it's also the point at which you commit to kind of a irrevocable step where you are now integrating your key components, and these can be very expensive components. You're now integrating your instruments into your spacecraft. And that is, I call that an irrevocable step because, and that's not quite correct, but that is the step at which you commit to potentially doing things with your instruments that make them harder to reuse for a different mission. So that is there's a gate review that we use there called SIR. That is the commitment to doing the system integration. And you also decide that you're ready to do those major integrations. You have all your processes, your steps, your integration testing, your facilities ready to go, your test plans ready to go. And so phase D is where you're doing the major integration. And then phase D, a big aspect of that, once you get the full, you can call it an observatory if it's designed to gather science data. We frequently use the term observatory, but at that point you've got your complete system together, and you do major environmental testing. So that's the environmental testing campaign. That's where we go into things like we vibrate the system to ensure workmanship. We vibrate it to loads predicted by the launch vehicle ascent. And then any major events that happen, such as separation events or Delta V, aggressive Delta V maneuvers, we will predict the mechanical environment that the system will face, and so we'll test mechanically for that environment. We also will test for things like RF emissions, whether the system is compatible with itself. Are there parts of the system that emit RF emissions that may impact another system or subsystem. So that's self-compatibility. And then we'll also measure for external emissions. Is the system going to emit externally, which has an effect on something else? So that's where we'll do that kind of thing. We also will potentially do acoustic testing. The launch is a very loud, it shakes the system also, but it also is loud acoustically. And if you have certain things in your spacecraft or your instrument that are susceptible to noise, think of it as a window pane. In a house, when you have a sonic boom over the house doesn't get damaged, but the window panes may get cracked or blown out. Well, spacecraft have things like that as well, where if you have something that's susceptible to acoustic damage, we will predict the acoustics, and then we'll do acoustical testing. And then the culmination of the integration and test activity is really the thermal vacuum testing. That's where we put the system into vacuum. We take it to the temperatures extremes that it will see in space, and then we test it through thermal cycle. So it will go to as cold as it needs to go and as hot as it needs to go. We will also do a type of testing to calibrate and confirm our thermal models, because we use those thermal models in space to when we're operating in space to make decisions about system operation. Whether we need to do pointing in a different way in order to achieve the thermal limits that we need to stay within. So TVAC, or thermal vacuum chamber testing, is one of the big important culmination tests, because at that point you basically will, after that point, you'll do closeout activities. You'll prepare the system to ship to the range, and then you'll ship it to the range, do whatever activities you need to do at the range. For instance, fueling will often be done at the range because you ship it without it fueled, but sometimes you will fuel it before shipping. Depends on the mission. But then you are integrating with the launch vehicle. So this phase D culminates in the range activities to integrate with the launch vehicle, and then do the launch rehearsals and launch. And then the gate that is happens towards the end of phase D, and it does happen before launch, maybe a month before launch, is we'll have an operational readiness review. And that's kind of the gate to close out phase D and declare that we are ready to launch, because that is the review that looks at our operations capability. The mission operations ready to go? Are the ground systems that will allow us to communicate with the spacecraft ready to go? Is everybody trained? Is everybody rehearsed their operations? And then once that ORR is completed, that's the kind of the final go ahead. There's a couple of last minute reviews around the launch vehicle being ready and the spacecraft being integrated and ready on the launch vehicle. So we'll have kind of mini reviews right before launch, but the ORR is the major gate review that declares that we're ready to go into operation.
So Butler,
yeah.
There's a question in the chat.
Okay.
Where would you view interoperability, unlike integration, in the project lifecycle, and why? ORR?
Well, there's various flavors of interoperability. So we will do interoperability between the spacecraft and the ground systems. Often, that'll be done in phase D, but it's not ORR. It's done well before that. We will, for instance, if I'll use the example of a Mars mission. If the spacecraft and instruments are intended to go to Mars, then when we're talking to that spacecraft, we'll use the NASA Deep Space Network. So sometimes it'll happen, aspects of that will happen in phase C, some will happen in phase D, but there's interoperability checks where we test that the radios can communicate to the DSN ground station. And so in phase C, that might be done at the radio level. So the radio is a component, not yet in the spacecraft, but we'll test either by sending the radio to JPL or in some other way, we'll test that the radio communicates with DSN properly. And then in phase D, we will have a van test where there's a mobile van that has all the RF equipment in it, and it can simulate in hardware a DSN ground station. And so the van will often come to wherever the spacecraft is. We'll arrange and schedule that. It comes to wherever the spacecraft is, and we will hook the spacecraft up to the van and ensure that the spacecraft as a complete system can talk to DSN. So that's examples of compatibility testing or interoperability testing. Another example is how the spacecraft attaches to the launch vehicle upper stage. So that is a interoperability test between the spacecraft and the launch vehicle, where, for instance, if we use a motorized light band as our separation ring between the spacecraft and the upper stage, then, and I've seen that done in a variety of ways, but at some point we will do a separation test either with engineering models of the hardware or often the actual hardware, where we will attach the two halves of the interface ring together, and then we will do separation tests where we simulate the spacecraft being separated from the launch vehicle. So that's another example of an interoperability test. Once again, that can happen in phase C with the component hardware, and it can also happen in phase D with the entire spacecraft. And a lot of times you'll decide what testing you do when based on the risk to the mission. So some testing is very benign, and you easily are able to do that in order to verify that your system will work. Some testing is quite dangerous, and it may not be something you are able to do. And so those are examples. I just called out a couple of them, but those are examples where we do interoperability testing at the either the subsystem or the system level.
All right, thank you, Butler.
Keep going, or more questions?
Yeah, keep going. We have about another half an hour, and then we just open it up for questions from the audience. So,
all right, we'll do. Okay, so this is a view of what I just talked about in terms of the phases, but this is kind of a classic NASA life cycle view of a mission. And so this is the standard project management approach at NASA. And we have a NASA requirements document in NPR. And I apologize about this, but when you get into the NASA world, you immediately start talking in terms of document numbers. So you'll find that a lot of us will immediately say 7120.5. And I won't do that today, but this is the NASA standards for how to do flight projects. And so you can see the phases at the top. You can see pre-phase A, phase B, C, D. And then you can see our operations phases, our phase E, and then closeout is phase F. The red diamonds, or red triangles in there are the gate reviews. And you can see there's parallel tracks. And this is because NASA traditionally has had a one-size-fits-all approach to this. And that is starting to improve, but that is still reflected in a lot of the things we do. And so in this chart, you can see that. This chart is intended to be everything for everybody. But you can see that there is a line kind of in the middle that says Human Spaceflight Project Lifecycle Reviews. Then under it, you can see there's one that says Robotic Mission Project Lifecycle Reviews. So those are different. There are some places where they overlap. You can see the similarities, but there are other places where they're very different, because human spaceflight is very different from robotic spaceflight. Some of the reviews are the same name, but what happens in some of the reviews are very different. So this chart is a good example of NASA attempting to do one size fits all, but then within the details, you find that it doesn't actually do that. And then we have mission classifications ranging from phase A, class A through class D. Those represent either the expense or the importance of the mission. And so class A typically is human spaceflight where human lives are at stake, or class A can also represent a significant investment into a science capability, such as a great telescope, one of the great observatories. So Hubble Space Telescope or James Webb Space Telescope, those are examples of class A. And then you get class B missions, which are typically larger missions. In our world, those would be billion-dollar class missions. Those are missions where it's a huge expense, it's a huge investment in science capability, but it may not have the lack of. I'm struggling with how to call it. Phase B missions are not less important than Phase A. It's just the stakes are such that you can accept a slightly more risk. So in Phase A, the risk tolerance is extremely low. The system has to work, either because you have human lives at stake or because of the importance of the asset to the country. Phase B are not much relaxed from that. You still have requirements for redundancy within your system. So the missions are a significant enough investment that the loss of the mission would be a great blow to science. Those are Class B. Class C are where most of the NASA science missions are done. So these are the routine science missions that NASA does in earth science, in planetary science, in heliophysics, and in I'm missing one of them. Oh, astrophysics. So Class C is where the workhorses are. So in Class C, you have more tolerance to failure. You're allowed to do single string missions, which can, are susceptible to single string failure. But you're encouraged and can do redundancy in your system as makes sense. And then Class D is where a lot of the innovation is happening within NASA. So in Class D, that allows much more risk tolerance. It allows much more flexibility. Class D is often used for things like technology missions, where you're proving technology. It's also done for missions where the program that is sponsoring the mission has goals that they want to do, where they want to take pretty aggressive risks and are willing to lose the mission in order to achieve their goals. So that's Class D. So you can see that while the facade may be that one size fits all, they're very different missions in these different classifications. We already talked about this, the key milestones associated with the phases. And then I'm going to go into how you transition. So you go through the gate reviews, which will often have associated key decision points, and that's what allows you to go through the gate review. So this is a chart that summarizes what I mentioned to you, that completion of these gate reviews like SRR or PDR or CDR, and then ORR is what takes you out of Phase D. Those are the gate reviews and will have associated key decision points with them. They're just one chart that shows what I was talking about. Now, let me go into the difference in project sizes. So flight projects range many orders of magnitude, from very large missions that are flagships or great observatories to very small missions that are CubeSats. And I've got some examples on here. You can see at the top left photo, that's James Webb. You can see a Mars rover mission on the right. You get to a MidX class mission in the left, and then you can see some of the CubeSat missions, either 6Us or 1Us or 1.5Us in some of those photos. And I mentioned to you the different classifications, Class A, B, C, and D, and the workhorses for the agency. The ones that get all the press typically are the larger missions, the Class B or Class A missions. But the workhorse missions that you'll often hear about in terms of the science productivity and specific science goals, those are the Class C missions. Okay, so the other thing that NASA, I mentioned that the one size fits all is kind of limiting in some sense. We used to have this rule that anything that went into space had to be managed under this first area, the NPR that I mentioned in that chart. But we were running into, years and years ago, we were running the problem that a lot of times you'll want to send something into space to test the technology. And you don't have to design it so it can't fail, because the whole point of testing technology is to gather data on it and see how well it works. So the one size fits all was a problem for technology development. And there has been attempts at adjusting that management model over time. And then one of the recent improvements in that is enhanced tailoring guidance. So you're able to tailor these missions. But in the last, I guess, 10 years, I'd say it's within the last 10 years, there's an alternate approach that NASA has been using, which has a different number. So once again, apologies, but instead of a .5 mission, you'll hear it referred to as a .8 mission. And that's how to manage, that allows you to manage spaceflight missions that are intended to be research and technology type missions. So the goal is not to gather the science data or the goal is not that the system gathers information and so the system is a tool. The goal of these research and technology programs are that the system is testing technology. So you either are testing a spacecraft or you have a kind of a generic spacecraft carrying a payload and you're testing that payload. And so we've been using .8 a lot more lately. And in fact, it's typically been smaller missions. In our world, that would be, 30, 40 million and lower for mission lifecycle cost. But recently, there have been some very large missions that have been done under .8. Viper is the best example. That's a multi-$100 million mission, but that was actually done under .8 because it was a technology demonstration mission at heart. And so these are the two major groupings. And then the .8.
So Butler, there was a question. What's the major difference between NASA project standards and European project standards?
Actually, they're very similar. And let me go to here. European standards, ESA or UKSA or CONES, they have very similar approaches like this. Their pre-phase A and phase A are done slightly differently. They have the same goals, but the way the European agencies fund mission development, those are slightly different. They have different gates that they go through to approve missions at the next step. But I would say once you get into phase B and then phase CD, the European approach is very similar to NASA. We've all converged, mutually converged on best practices. Now, within those phases, you do have differences. The European standards on quality assurance may be equivalent to what NASA does, but may be done differently. And I can tell you honestly, NASA considers the ESA standards to be equivalent or better than the NASA standards. So usually, if there's a European component contributed to a NASA mission, NASA doesn't impose our own standards onto that component. We accept the European standards because they're considered as good or better than the NASA standard. So these phases are similar. I would say the biggest difference is in the concept development phase because European agencies do that type of investment and decisions slightly differently.
Thank you, Butler.
Okay, sure. And then getting back to and I'll close this in a minute. Getting back to the .8, if you compare the chart I showed you previously with the red triangles, you can see that there's fewer triangles here. So that means that you have different and lesser gate reviews. And so because your goal is technology development and research on the technology, you won't need a lot of those gate reviews. So you'll see that this is simplified. And also it's very tailorable because you can scale things down as the program that is sponsoring the project wants to do. So the programs can say, I don't want these gate reviews, or I do want these gate reviews. And at the extreme, you can have a mission which are termed do no harm missions. So those are missions that their only requirement is that they don't harm somebody outside themselves. So the mission can't harm the launch vehicle. So if the mission launches with other payloads in a single launch vehicle, this mission can't harm the other payloads, it can't harm the launch vehicle, but there's no constraint on it doing harm to itself. So obviously the sponsors of these projects do want them to achieve some goal, but in this case, you don't have a lot of the requirements that are designed to protect the spacecraft from itself or to protect the goals of the spacecraft. Do no harm missions can be very lightweight, and that's at the decision of the sponsoring program. All right, similarities between the mission classes. So the complexity of interfaces. So this is one that often surprises folks, but if you think about it, it makes sense, and I'll talk about it in a moment. But CubeSats and small sats, and by small sats, I'm talking about the few 100 kilogram type of missions. So obviously you get into 1,000 kilograms, couple of 1,000 kilogram missions. Those are larger missions. They're not really called small sats. But when I say small sats, I'm talking about the few 100 kilogram class mission. If you talk about complexity of interfaces, the very tiniest CubeSat and small sats and even larger spacecraft often have the same number and complexity of interfaces. So that's often a surprise to people. System engineering. So we have system engineering principles that we follow. We talked about requirements flow down. I think later you'll see a webinar about model-based system engineering as a new approach and new tool that we're using. Systems engineering is important across all of these mission sizes. Even for very small teams, the principles are still important. The size of the number of staff and the number of analyses you do may change, but the system engineering principles are still important. Operations. When you talk to mission operations folks, they say, well, to us, all missions, no matter how big they are on the ground, are just points in space. So for operations, when they're talking to a spacecraft, they don't care if it's a CubeSat or a 1,000 kilogram spacecraft. To the ground antenna, it's just a point in space. So the operations can be streamlined and slimmed down based on the risk posture based on how much automation is used or onboard autonomy is used. But still, operations is needed for all these mission classes. And then, similar to the complexity of interfaces, the systems block diagram are smaller. The components are smaller, but the diagram is often the same. And so let me go into examples of that. Oh, well, before I get to the example. So the differences. So I talked about similarities, differences. Small missions have fewer cost reserves, if any. Larger missions have intentionally funded schedule reserve and schedule margins along their development path. Smaller missions typically don't do that. They have, if any unfunded margin or slack at the end of delivery. Range safety. CubeSats are encapsulated and usually have inert propulsion systems with less stored energy. So range safety is much simpler for them. Small sats with larger propulsion systems are often mounted in ways where they're exposed to more vibration. They often have prop systems with significant stored energy, and so they have more range safety requirements. Flight dynamics. This is designing your trajectories. Flight dynamics for CubeSats in low Earth orbit can leverage GPS, so it makes flight dynamics and trajectory monitoring and predicting much simpler. Once you get into deep space, you're dependent on ground tracking and ranging and orbit determination analysis. So flight dynamics is much more complicated once you get into deep space. Attitude control. In low Earth orbit, CubeSats or spacecraft, or even small sats in low Earth orbit, can take advantage of the Earth's magnetic field to manage momentum. So you can use mag torquers or equivalent to dump momentum that would otherwise build up. If you're in deep space, there is no such advantage. So you need a means of dumping momentum, and that means you're using thrusters to do that. And then the final difference is the ground support equipment, GSE. The approach to that are very different because size is very important. So how you do lifts, how you do transports are very different. I'm not gonna spend time on this, but this is just a visual example of how schedule is treated differently, where larger missions, you'll have those green slide areas are where you have margin embedded in your schedule at appropriate points. Because when things come together, it represents expense. In smaller missions, you might just hold it all at the end. System complexity. So this is where the system block diagram. So I've got two of them here. One of them is a small CubeSat, and one of them is a larger mission, a mid-X class mission to the left and the CubeSat to the right. You can see that a lot of these diagram system level interfaces look very similar. So the connection between your command and data handling system to the other parts, you have those interfaces across the board. You have radios across the board. You'll have electrical power across the board. All of those things, you'll have payloads that both missions have to support. So you can see the similarities of the system block diagram. The number of interfaces, complexity of interfaces is very similar. The one difference that you can see is in propulsion, because propulsion can be either non-existent on some CubeSats, or it can be very simple propulsion. Whereas in larger systems, you have high pressure tanks, you have fuel and oxidizer tanks, you have higher complexity of the propulsion system, and you have a lot of stored energy. So this is a kind of a visual way of identifying the similarities in interface complexity, but also the differences in some subsystems. Launch accommodation. I mentioned launch accommodation can be different. Typically with small sats and larger, you either primary or a co-primary on a launch vehicle. So that means you're the majority user of the fairing space. So you might have other things with you, but you are the primary in most cases. the launch accommodation is very different for smaller small sats and CubeSats because in the middle diagram, you can see that those small sats circled in red, they are mounted cantilevered to some launch adapters. And you can see the primary may be at the top, and then you've got these small sat boxes in the middle. And you can see that the type of loads that they have to take, especially the cantilevered loads against the launch ascent, you can see that that would be very different than if you're in line with the thrust as the primary. Also, if you go to the right, you can see the CubeSats. Those are launch dispensers there, those red colored boxes. The CubeSats are inside those launch dispensers. So those are encapsulated. So not only are they protected from a lot of the environment within the fairing, but their vibrations and shocks can be supported by an external frame, which is the dispenser. So you see that the launch environments can be very different across these. I mentioned ground support equipment and ground handling. So critical lifts are, NASA defines critical lift is anytime you're lifting in any way, lifting an object that either there is a safety aspect of it to the people around it, or the expense of the thing that you're lifting, or the criticality to the mission. Those are all identified as critical lifts. So critical lifts have a lot of preparation and a lot of practicing around them, but you can see the difference. Critical lifts for a CubeSat, and so this is a 6U CubeSat that's being inserted into the launch dispenser there. That is a critical lift. But you can see that's two people holding the spacecraft and manipulating it. Once you get into the 400 to 1,000 kilograms, critical lifts are different. You use cranes and you position them with special ground equipment. When you get into the large spacecraft, the great observatories, critical lifts are immensely complicated events, and sometimes you'll build entire facility capability around a critical lift event for a space. So you can see that those are very different. You have critical events across all mission sizes, but they can be very different. Transport. Transport for CubeSat to the left. You can see those are the loaded dispensers there, and you can actually put them in shipping boxes and ship them to the launch. For MidX and some larger small sats, shipping can be very different. That's to the right. You can see a truck transport that is intended to go cross country. There is a shipping container that is a specialized shipping container. And then that shipping container, you can see the environmental control equipment that is towards the end of the truck, the back end of the truck, that maintains the temperature, humidity. You might have shock isolation. You might have other things in the transports. These apply to truck transports like I'm showing here, but also to ship transports. Sometimes you take them over water, or air transports. Sometimes you'll take a large cargo aircraft and transport the spacecraft cross country. So you see those are very different. Craig, in the interest of time, I'm going to not talk about this. This is my current mission. The only reason I wanted to bring this up is I wanted to show an example of a mission that had aspects of all of this. So this is a mission where we have a large spacecraft that's the mothership, but it has 8 small sats attached to it. And these are small spacecraft that deploy once we're in orbit, and it forms a swarm mission. So this is interesting in the context of what I just said, because the whole mission is an observatory. It consists of a large spacecraft plus 8 small spacecraft. So it has some of the aspects of all of what I talked about, some of the large spacecraft aspects and some of the smaller spacecraft aspects. So this is just a amusing thing to show how the swarm flies. They all fly in a high Earth orbit that gets near the moon, but it's the relative orbit between the elements that's important. I'm rushing through that. So anyway, just to close out some of these, small sat missions are more expensive than CubeSats. So they have organizational priority. Small missions have a lack of key tools to solve problems. Small missions will also often have fractional staff rather than staff dedicated to the mission. And then typically I find that smaller missions, you'll have a breadth of staff expertise, whereas the larger missions will typically have more depth. So small missions, you'll have multi-talented individuals working on it that cover broad technical areas, but in larger missions, you can afford to have deep experts in any particular domain. And this is just a humorous approach. This is my assessment of which are harder to manage. Smaller projects, difficult to staff, they're brittle to problems, you have fewer tools, so you're often dealing with problems all the time. Larger missions have much more complicated organizational structures. They have an execution inertia, so are less nimble. There's definitely more politics, and this is common across the board, NASA as well, US as well as ESA and European. When they fail, they tend to fail very spectacularly. And when they fail, typically the project manager is the sacrificial lamb. So they're very technically similar, but the increased size and complexity, size and cost brings added. So that's, I'll close there. That's what I wanted to convey today. Sorry about rushing through my own mission at the end.
No, thank you very much for a wonderful and an presentation, Butler. It was really great to see your take on the project review cycles. There was one question in the chat, and I know we didn't have time to get through all the questions in the chat, but we will address those and provide written responses to those questions that we missed. But one I think that kind of ties back into the first webinar of this series was, what specific tests are performed during ORR to validate the integration of a CubeSat system?
Well, ORR is a review that determines whether you've done all the testing that you need to do. So ahead of ORR, we will typically have testing that either proves out elements of the mission operations ground systems, or trains the team, or rehearses. And so you'll have, and there are various names for these. The ones I'm familiar with are, you'll have thread tests, where you're taking a particular thread of operations and you're testing that thread of operations end to end. So it might be something like momentum dumping. So you're testing how operations commands and manages dumping momentum on the spacecraft. So you'll have a thread test where you try that out, that thread. And then you'll have engineering readiness tests where you typically will have a majority of the ground operation system available, and you will both be testing the system in terms of whether it functions right, whether the ground operations system, the ground assets, whether everything can talk to each other, whether information can flow, are the operations interfaces the human operators are looking at, do those work? You're also doing some training on your operators during these ERTs. And then ultimately all this results in rehearsals. And so you'll do rehearsals that are both nominal rehearsals and off-nominal rehearsals, where you're practicing dealing with emergencies and anomalies. And you'll do those rehearsals with the ops team in a very similar fashion to how you're actually going to fly the mission. And in some cases, you actually will do it at the same hours that. So if your mission requires you to do something at 1 a.m., you will rehearse with the team doing that at 1 a.m. in order to really practice. ORR is kind of the end of that, where you will have completed all your thread tests, all your engineering readiness tests, and probably most of your rehearsals. But after ORR, it's typical that you're still doing launch rehearsals. So you're still doing mission operations rehearsals for the launch aspect. So ORR is the culmination of the testing, but the testing occurs mostly before it and then a little bit after.
Okay. All right. Thank you, Butler. So I'm going to open up the floor. So if you do have a question for Butler, if you could just raise your hand, we'll take the next 20 minutes to take some online questions. Okay. Go ahead. Friedra? Oh. Ricky. Yep. Ricky, can you unmute them?
I'm going ahead to give them available to unmute themselves.
Okay. Ricky, are they still muted?
Yeah, they have to unmute themselves. I've
Okay.
given them the ability to unmute.
Okay. Yeah, the folks with their hands raised, if you can unmute your mics and ask your question.
Well, while we're waiting,
Okay.
I can see the chat questions. I'll try to answer a couple of those real quick, and then
Okay. All right.
you're figuring out the microphone. So
Okay.
I see one is about do we use agile or waterfall methods for project management? Those are often used in the software aspect. So software development for our flight software and our ground software. We will use some software development techniques like agile or waterfall. I would say for managing the whole project, it's probably closer to waterfall methodologies, although those terms are more often used in the software world. But in project management, I'm familiar with how software is managed in those methodologies. So I would say managing a flight project is closer to a waterfall methodology. And then there's a question: have AI tools become part of NASA's project management? We're looking at that. I would say that's not prevalent yet, but NASA has rolled out some AI support tools across the agency, and a lot of folks in the agency are looking at those tools or how they can benefit. So I'd say they're not prevalent yet, but they're definitely coming on board, and people are trying things out now. And I can't remember the name. There is the agency has rolled out a couple of chat-like tools, but I don't know what the underlying AI tool that the agency accesses under that. Apologies.
Okay, so there was another one. Can we jump one phase to reduce in order to reduce cost or delay?
Yes, you can. In Class D missions, you definitely can do that. That's frequently done. In the .8 missions that are research and technology, that's frequently done. Where in the .8 missions, you'll often have just the equivalent of a design review. It's not even called a preliminary design review or a critical design review. It's called a design review. And so in .8, you'll have that. In Class D, you can sometimes have that. My favorite one to skip is the systems integration review, because I often manage phase CD not as separate phases, but as a single phase, CD. And the reason is that the old NASA style of separating phase C from phase D, that was intended to kind of produce all of your hardware, all your expensive stuff, and then take a pause and decide, am I ready to put everything together? Well, you'll often have things like radios. Radios are a classic example. Radios will often come late. And so if you have to wait till everything's ready to do your pause for your SIR, then your schedule becomes insanely long. And so modern days, we will start integrating as early as things start arriving. So if you start to get components of your avionics suite, you'll start integrating them together. If you start to get your propulsion systems come in, you'll start integrating those together. And if you have anything late, you will sometimes go into environmental testing with mass models of the thing that's late, and then do what's called a penalty test afterwards, where it's a subset of testing once you get the thing and integrate it to catch up to the rest. Those things, as we're doing to optimize schedule, those things completely blur the lines between phase C and D. So that's why I will often try to either have flexibility and have SIR occur at a different place, or if I can talk the program sponsors into it, I'll try to skip SIR entirely. But yes, you can skip or optimize reviews in order to make the schedule shorter and to have the costs less.
Thank you. So anybody with their hands up, can you unmute and ask your question?
Yeah, let's try and go to Senzo.
Okay.
Just go ahead and unmute your microphone. It should be a link at the top of your window. If not, let's try Hassan, if you can unmute your microphone.
Yes, I think now I'm okay. Can you hear me?
Yes, we can. Go ahead, Senzo.
Okay, great. My name is Senzo. I'm from the southern part of Africa. I wanted to ask a question based on the previous slide. Maybe if you can go back one slide, Butler.
Yes.
Yes, on the smaller and larger projects. To say, would you advise one to say, instead of designing a larger project, break it down into smaller projects and then launch it in one vehicle? Probably try to have these different missions and then or different small sets to do those missions, and then you can deploy them as small projects instead of having one complex big project.
Let me repeat the question and see if I understand what you're asking. You're asking if the small CubeSat style projects, you can do things incrementally rather than have everything in a larger mission. Is that what you're asking?
Yes, like try break the larger mission into smaller missions.
Yes, that actually is an approach that is interesting, and there's been some investigation of that, where you will have a broader goal, and then you'll decompose it into smaller elements that might be individual missions, and then the individual missions work together. So that can be done. It's very dependent on the mission class. The Helioswarm mission that I mentioned is an example of that, where of the 8 smaller spacecraft, those are developed independently of the large spacecraft. They're brought together at the end, where we basically mount everything together ahead of launch. But it's a single project, but we have very distinct elements within the project. And then beyond that, you might have a mission where you will launch some components of the mission into Earth orbit early, and then you will have other components in development, and then those are launched later, and you will build up your capability over time. That is sometimes done in Earth science missions. We haven't done a lot of that in deep space missions, although oftentimes you'll have, like Mars missions, you'll have not a single project, but you'll have a single program that has a goal that may involve sending a communications relay around Mars ahead, and then have another mission in development that goes later, but that then takes advantage of that communications relay to, say, orbit Mars or land on Mars, and then relay communications. So those are some examples of what you're talking about.
Okay. Then what would be your advice on building a pocket cube or a small satellite from off-the-shelf equipment?
So how to build a small sat or CubeSat mission off the shelf from components?
Yeah.
There's actually,
Yeah, like a pocket
Yes.
cube.
yeah, there's one of the things that's interesting in the CubeSat world, even in the larger 6U or 12U CubeSat world, is they have almost become commoditized, and there's a large support community industry that builds components and things. So you can these days either order complete CubeSats, or you can order CubeSat components and put them together yourself without having to develop anything yourself. So that's a huge benefit of the maturation of the CubeSat community around the CubeSat standards. And I would say that is now extending into the larger domains where you have standardization, definitely around 6Us, and I would say standards around 12Us and larger are quite common these days. So that allows you to use the commercial off-the-shelf approach and either buy complete systems, or and then you integrate your payload to it, or you buy all of the components and then put it together yourself. And in the small set, the larger small set world, that actually is extending up into the small set world as well, because a lot of these vendors which offer small radios, for instance, that will work with CubeSats, also offer larger radios that are suitable for larger small sats. And so we're moving farther away from the old world where for NASA projects we had to build everything ourselves. Now we can actually order a lot of things from a robust commercial capability.
So
Okay, our next person up is Hassan. You can go ahead and unmute, and after that would be Nava, would be next. Hassan, can you unmute? Okay, let's try Nava. Nava, can you go ahead and unmute and ask your question?
Hi, my name is Antoine.
Hello?
Yeah, go ahead, Antoine.
Yes, well, I would like to thank Dr. Butler on all the presentation. It was great. We learned something new about NASA's missions and the strategy they take to launch small satellites or cube satellites, or even Class A missions. And I have one request. If we can contact Dr. Butler, if he can send me his email or something like that.
yeah, if you could just send an email to the UNISA web address, I think Mommy will post it, and then we can get you in touch.
Okay, please. Thank you.
I see a couple of questions in the chat I can answer while folks are working their microphone. There's a question about similarity between NASA project methodology versus Project Management Institute. Does NASA use PMI? I don't actually know where PMI came from, but I can tell you that there is a large overlap. NASA has the equivalent of PMI certification that our project managers are expected to do. So we have, it's called OMB FAC certification, and especially for the large projects, NASA requires the project manager to have a certification like that. So there is a similarity. I actually don't know if PMI was born from NASA methodology or not, but we have a large similarity. And then another question was, what are key performance indicators or metrics used to evaluate the success of a CubeSat project during the review phase? We will have KPIs identified by system engineering that we will track. And so we'll have during development. Now, I'm not talking about after launch when we're evaluating the success of the CubeSat. That's based on the goals of the mission. But during development, we will often track KPIs that are things like the mass against the mass margin. So we'll identify margins for every system in terms of mass, power, data, thermal, mechanical. We will identify margins, performance margins up front. And then as the system is developed, so for instance, mass is one of them, we might allocate 10 kilograms for a system. And that represents our best guess at the beginning of the thing that we are buying or building might be 8 kilograms. And so we will allocate 10 kilograms to it so that we have a 25% margin on that. And then during development, we will track the actual mass as we put the system together and get an idea of how well we're doing against that total 10 kilograms. Because when you're putting together your first guess, it's very common to forget things like harness, electrical harness. You may have a guess at how heavy a harness is. When you actually put the harness together, it's very common for the harness to have more mass than you expected. And so as we put the system together and start weighing it and measuring the mass, we will start using that margin. And so that will be a KPI. Power is another area where, especially heater power for thermal management. You will guess what heater power you need for thermal management. We'll apply a hefty margin to that. At least for the larger missions, we typically will apply a hefty margin. And then as we get our thermal models, detailed thermal models developed, and as we get TVAC results calibrating those models, then we'll get more certainty around how much power we need to apply to heaters to stay within our thermal range. And we'll have a KPI around heater power, for instance, or power in general with margin, and then we'll show how we do as we get more certainty. So yes, those are some of the KPIs that we use.
Okay, so I see DM Garcia. Can you unmute your mic and ask your question?
Yes, I'm trying to. I believe I'm on mute now. Thank you very much, Mr. Hein, and to the organizers, to this great conversation at the United Nations level. This is fantastic. My name is Diego Garcia. I'm originally from Colombia in South America, but I'm based here on the Space Coast, close to Cape Canaveral, and working with the Aerospace Medical Association. My question is more about human exploration, and that might be a little bit outside of your scope. But for example, NASA HRP, the amount of science that is coming out from the human performance research and of course the amount of resources. But then a good example of that is the SOMA Atlas is actually is a whole issue of the Nature magazine talking about omics in space. Again, a lot of budget, a lot of good science. But then at Kennedy and Johnson's, flight surgeons are clueless about how to work with these new science, how to actually, bring that to operation. So from a systems engineering perspective, how NASA can do a little bit better, like buying their own product, as your colleague at Ames, Dr. Emmanuel Barshi, would say.
Well, I'll admit that that's a bit outside of my expertise area. I specialize in robotic missions, so I don't have a lot of insight into the human missions. Like you said, a lot of that is done at Johnson Space Center and Kennedy Space Center. I know there is a lot of research and interest in human performance in space. I just don't know a lot about it myself. So I think you have already identified the resources that are probably the expertise areas at NASA Johnson and Kennedy Space Center. I would refer you to them for that type of answer.
Okay. Thank you, Butler. So we have time for one more question.
Hello.
Oh, yes. Go ahead.
Hello. My name is Sunul Prasan from EM1 Thailand. Thank you for your share your experience. My question is related about the regulation. In your experience, which phase of the project Right Circle more related with the regulation like FCC or ITU for NASA, and how?
Yes. So flight missions are definitely under regulatory oversight in various ways. In the U.S., we have oversight from the Federal Communications Commission (FCC) and then the Federal Aviation Administration (FAA). We also have some oversight from Commerce and State Department and around things like we have oversight around environmental issues. But I would say FCC and FAA are the two major regulatory oversights that we work with. FCC regulates the RF spectrum, and so for CubeSat missions that are done under NASA sponsorship but outside of NASA, typically the FCC regulates. For NASA missions that are managed by NASA, and especially the larger missions, those are the spectrum regulation is from NTIA. So if you're so there's really two worlds, and the FCC world approval is different than the NTIA approval. NASA works NTIA approvals with the regulatory body that's international, while FCC is just covering within the U.S. In the FAA, that is often regulatory for launch vehicles and things like that. And then we'll often have regulatory aspects around environmental protection. So flight projects have to go through National Environmental Protection Agency, NEPA, approvals for the things that we do. Typically, that's not onerous for smaller missions, but that can be quite onerous for large missions, especially if they have radioisotope materials involved, or there is some major facility impact on the environment around the facility. So those are some examples. But yes, we do have regulatory oversight, both national in the U.S. and international.
Right. Thank you very much.
Okay. Thank you, everybody. And thank you again, Butler, for a wonderful presentation. And thank you all for attending this webinar today. We look forward to seeing you at the next webinar in January. And have a great day, everybody. Thank you very much.
Bye-bye, folks. Thank you.
Thank you.